Good afternoon, everyone. Everything is theoretically impossible until it is done. Welcome to 95th episode of Creative Online Talks. Myself, Supriya Naika, hosting this program. We gather once again to celebrate the spirit of curiosity, the hunger for knowledge, and the power of collective learning. Creative. Creative is a group of people who are eager to gain new knowledge, and cre means creativity, active means activeness. To be active, we need creativity. Creativity keeps us active. Knowledge Square is our tagline. Sharing of knowledge increases our knowledge. Vision of creative is to build a constructive thinking on various domains. We mainly focus on non-textual, non-academic, non-syllabus related concepts. Every Saturday, we organize online talks on various topics, and we live streaming our program on YouTube channel around 3 to 4 p.m. on Saturdays. Today's creative topic is X-ray crystallography and its application. In this session, we will explore the fascinating world of X-ray crystallography and discover how this Okay, some network issues. Okay, sorry. Uh, in this session, we will explore the fascinating world of X-ray crystallography and discover how this powerful technique has revolutionized the field of structure biology and material science and its wide-ranging application. We encourage participants to actively participate, ask questions, and engage in discussion at the end of the session. I call Govardhan, creative volunteer, to introduce today's speaker. Over to Govardhan.
Good afternoon to everyone. My name is Govardhan. It is my great honor and pleasure to introduce Dr. G.N. Anil Kumar sir. Dr. G.N. Anil Kumar sir, born and brought up at Gudibande, completed his BSc from National College Bagepalli and MSc from Bangalore University. He has obtained his PhD in chemical crystallography from Bangalore in 2012. His research interests include single crystal and powder diffraction studies on organic and inorganic materials, co-crystal design and ab initio studies of solids. He has 20 years of teaching and research experience. He has published more than 50 research papers in international peer-reviewed journals and completed a VGST-sponsored research project. He guided one PhD and guiding one more student for PhD under VTU. He also guided several UG and PG research projects. Thank you so much, sir, for coming and bestowing us your warm presence and welcome to the fifth session of Creative GVD. Thank you, sir. Over to Supriya.
Thank you, Govardhan. Over to Anil, sir. Anil sir.
Madam, any issue is there with the connectivity with Anil Kumar?
I'll call him, sir. 1 minute.
Now, can you hear me?
Yes, sir. Go ahead, sir.
Hello.
Sir. It's audible.
No, technical issue. Yeah. Can you hear me, ma'am? No.
Yes, sir.
Am I
Yes,
audible?
sir. We are. Yes, sir. Yes, sir.
Just check the. Am I audible?
Yes, sir. Yes, sir. Go ahead, sir.
Hello.
You can
Am
share
I
your
audible?
PPT, sir. Yes, sir.
Anil, you are audible. Please go ahead. If my voice is audible to you. Supriya, is my voice audible to you?
Yes, sir. Yes, sir.
Maybe then there is issue with Anil
Yes.
only. You can log out and log in.
Maybe network issue. 1 minute, sir.
Hello.
Anil, your voice is
ಬಟ್ ನನಗೆ ಅಲ್ಲಿಂದ ನೀವು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಿಲ್ಲ.
Anil, is our voice audible to you? Please log out and log in.
ನನ್ನ ಫೋನಲ್ಲಿ ಕೇಳಿಸ್ತಾ ಇದೆ, ಬಟ್ ನನಗೆ ಆ ಕಡೆಯಿಂದ ನಿಮ್ಮ ವಾಯ್ಸ್ ಏನು ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. Shall I go ahead with? Okay.
So, screen is visible. Is this?
Yes, sir. Your screen is visible.
But his voice?
Okay. I hope all of you are hearing me.
Yes, you are.
I don't know. I have some issue with the microphone, but I'm not able to hear the organizers. Anyway, I will just continue. So let it resolve, think later from your side. I'm very happy to be part of Creative to share my little knowledge, whatever I know about the X-ray crystallography. So I'm practicing this field for many years. And I'm sharing with you how crystallography is useful. So in characterizing and also in helping us to understand the matter. So the outline of my presentation today is introduction to the crystallography. I'm happy that many of the experts also there in the who are working in crystallography, like Jyoti Madam, powder diffraction technique and single crystal diffraction and applications of the both the techniques. So today we are using a variety of diffraction techniques. Among them, the mainly X-ray powder diffraction, single X-ray diffraction, reflectivity, small angle scattering, atomic pair distribution function, XRF, XRM, and so on. So among the many of these complementary techniques, so powder XRD and the single crystal XRD diffraction technique are very vital in revealing the structure information. So the impact of crystallography across the years since from 1912, after the discovery of diffraction by Loewe and Bragg, so it has actually contributed a lot to the many fields and bagged many Nobel Prizes also. This is the list which I listed from IUCR, International Union of Crystallography. So you can just see consistently seeing many Nobel Prizes are awarded in the field of physics, chemistry, physiology, or medicine, starting from the discovery of X-rays from 1901, Röntgen. So the crystallography is nothing but a branch of science. It deals with the study of arrangement of atoms in crystalline solids. It finds application in many disciplines, including physics, chemistry, geology, biology, material science, many other fields also, even the material science and so on. So why it is so important for us, the crystallography? Because if we understand the function of a structure of a material, we can predict its function. So the structure and properties are always interrelated. Whenever you design a new material, such as a drug, alloy, or any other compound, so people look for the important properties. So it may be a chemical or it may be physical property. So these are very useful in designing materials for various applications. So among now the crystallography is limited to only the crystalline material. We know that the materials are broadly classified into gases, liquids, and solids. The solids further classified as the amorphous and crystalline. And the crystals, we come across the polycrystalline materials, single crystals. So polycrystalline materials means they are those available in not a regular form. So maybe of many small crystallite grain kind of thing. Whereas the single crystals are defectory and they are specialized methods to grow them. And quasi crystals are somewhat interesting materials which are not perfectly amorphous or the crystalline. So they exhibit a short order and the higher order symmetry. So crystalline and amorphous materials are broadly, if you just look into the internal structure, so what makes a crystalline material is regular and periodic arrangement of atoms, such as the diamond. Suppose if the atoms are loosely packed but not arranged regularly and randomly they are distributed, so then it forms a amorphous material. So example is the glass, which is amorphous, highly amorphous in nature. So we know that the crystalline materials have the important properties like melting point, fixed melting point, and some anisotropy, etc. Whereas the amorphous materials, they do not have anisotropic property; they are isotropic. Also, they do not have a sharp melting point. So now the question is how the atoms or the molecules are arranged within the unit cell. So because we need to understand the structure of a material, so therefore we need to understand symmetry. So to understand symmetry, I'm just making use of the Escher diagrams. Here in this picture, you can notice the horses. So one is red and the white, and it is packed such a way that all are identically packed without leaving any voids. And you can see the orientation of one horse, white horse, everywhere it is same. Its shape and its position. So everything is perfectly ordered, so that there is no gap in space if you repeat these horses infinitely. Similarly, you can see here also some interesting cat which is having wings, and you can see this packing is also somewhat symmetric. But these cats are arranged in line now, so it is translational. So you move one cat periodically. So yellow cats you can generate. Similarly, you move that block cat in the backward direction, you can generate these packing infinitely. In this diagram, we have three types of objects. So you have a bird, and then you have a fish, and you have even a crocodile. But they are designed in a different manner. So here packing is different, but this is also filling symmetry. Earlier also the packing is different, but that is also filling the space without leaving any void. So in solid materials also, the atoms and molecules are actually packed in the same manner. So it may be translational, it may be higher order symmetry, etc. But these we can understand these in terms of space group, point group, etc. So on. But now, instead of drawing these complicated diagrams, you can have a shortcut method. What is the shortcut method? You just pick the noses of 4 nearby white horses, and you can join them by a drawing, and which gives you uh, a shape, which basically a square in this case. And you take this square and you repeat this square in 2 possible directions, x and y direction. You can simply generate this pattern. So in crystals also, if the packing of atoms and molecules is arranged infinitesimally, but we can deal crystals with a small, this type of small units, which are called as the unit cells. So now generally, instead of looking at entire molecules which are arranged in the entire crystal, you take this type of the small component, that is unit cell, and you repeat these unit cell in space. Then you can generate the lattice. In this case, this is 2-dimensional lattice. But if you repeat this in 3 dimension, you get a 3-dimensional lattice. But the allowed geometrical shapes are maybe it is square, rectangle, hexagon, or triangles, but not this type of pentagons, octagons, and hexadecans, etc. Suppose if you choose these type of objects, it leads to voids, so that it will not repeat infinitesimally without complete packing. So these are actually not allowed. These are impossible symmetries for crystals. So based on these symmetries, so we can now differentiate, that is the unit cell, because every unit cell has a property. You can measure the length, breadth, and then height and angles. So if you take a cube, for example, all sides are equal, all angles are equal to 90. So it is said to be a cubic system. And if all angles not equal, all sides are not equal, then it leads to formation of a triclinic system. So on. I think this is very basic, and all of us know, we have studied in our basic degree. So, but the Brevet observed that, so if you combine these 7 crystal systems with possible lattices, such as primitive or side-centered or body-centered or the face-centered, we come across only 14 ways of lattices, only 14 independent lattices, which are independent. So these 14 lattices are actually called as Brevet lattices. If any material crystallizes, it belongs to any one this 7 type. So 14 crystalline lattices and 7 crystal systems. So finally, the conclusion is, if you have a material or a molecule or an atom, and the basic building block of the crystal is a unit cell, and the atom or a molecule will be packed in a symmetrical pattern within the unit cell. And if you repeat this unit cell in 3 dimension, it leads to a crystal. So this is how we look into crystal, because crystal is a regular packing with symmetry. So the atom or a molecules are packed in such a way that, so these atoms, it leads to the formation of the crystal structure. So in order to observe these atoms, so we make use of X-rays. So why X-rays are suitable? Why we can't see atoms by any other method? We can just make a comparison now with microscope and X-ray diffraction method. So this microscope basically uses visible light the light is the wavelength of order of 400 nanometer to around 600 nanometer. And since the wavelength of the light is much larger, so when we observe, the highest resolution possible will be in micrometer. But we know that atoms are actually packed in the solids at a resolution of few nanometers. So it is not possible to observe the that is position of the atoms within the unit cell or within the crystalline material using visible light, because wavelength of the light is larger. So therefore, we make use of the X-rays, because X-rays are having the low wavelength, and the wavelength of the X-rays is comparable to the separation of atoms in the solid. As a result, when you pass the X-rays into the crystalline material, so they undergo diffraction. But unfortunately, the light, we have lenses. But to focus the lens, we have focus the light. We can use lenses, and we can see the object directly. But in case of X-rays, because their frequency is so high and energy is very high, it is not possible to focus X-rays like light rays. Therefore, we get a information in the form of a diffraction, X-ray diffraction, and it's a pattern, and it represents the atomic arrangement on a photographic film. And so if you mathematically analyze this, so you can able to reveal information of position of the atom within the unit cell. So therefore, you need some expert to do this job. And nowadays, we are making use of computers, because it's several mathematical programs need to be used to analyze this data, obtained diffraction data. So a person who trained in this will be a crystallographer. And now I think most of the calculations is done automatically by powerful packages which are available freely also and commercially. So therefore, we need X-ray diffraction technique. So if you use X-ray diffraction, you can actually understand the arrangement of atoms or molecules within the unit cell. So therefore, we make use of the X-rays in the X-ray crystallography technique. So geometrical crystallography deals with arrangement of atoms and molecules, but the symmetry, unit cell concept, it is all about the geometrical arrangement. But the physical methods, diffraction, is actually X-ray diffraction. So physically, we can use experimental setup, which consists of the X-ray tube, which emits the monochromatic X-ray beam, and we have to shine this X-ray beam on the crystalline material, and so we get a diffraction pattern. So the basic principle behind the diffraction is the Bragg's law, because Bragg explained this. I think you can observe here, the X-rays are now falling on the crystal planes. So we can think of the atoms are arranged in crystal, and we can think of the linear array of atoms are actually placed in planes, and these planes are actually indexed by the Miller indices method. And suppose if two rays of X-rays falls on two convegative planes, and the ray one will reflect how the light ray interact with a mirror plane. Exactly, the ray 2 also reflect from the another plane. So, but when the two reflected rays travel, so both of them will have a phase difference. The phase difference is of d sin theta. So, if this difference is in phase, so there is a constructive interference. If it is out of phase, there is a destructive interference. So, whenever we get a diffraction spot here, so like this, and that is because of satisfaction of the Bragg equation. So Bragg condition. So this is the Bragg's law or Bragg condition. Whenever this condition is satisfied, we get a diffraction from the crystal. See, this is how we actually assume the crystal planes within the unit cell. See, the atoms are packed in the unit cell or in the entire structure, and we can think of the planes in a whichever order we want. We can. So this is a distribution of atoms. You can represent them in a particular type of planes, or you can choose inclined planes or any other direction. But using Miller indices method, we can identify the orientation and the type of planes. It is indexing method. So therefore, we can use this X-ray technique for identifying the location of atoms within the unit cell. So if we use a single crystal, a crystalline material, the pattern looks like this. So which is I have shown in the first diagram. If it is a disordered structure, not poorly packed structure, then the pattern look like this. If it is a microparticle or nanoparticle, nanoparticle or nanopowder, the diffraction pattern will be look like this. Or if it is amorphous, then there is no diffraction at all. So we can just simply see this type of things. So this is the comparison of how diffraction takes place from the X-rays. So X-rays, without X-rays, we cannot reveal the structured information. It is so important because the X-rays were discovered by Röntgen accidentally. So then the Lowe, who actually observed the X-ray diffraction from a single crystal, and interpretation of the diffraction using the Bragg's equation was actually done by both Bragg's father and son Braggs, W.H. and William Bragg. So these made a revolution. So because they showed how to index the indices by using Bragg equation, how to identify simple lattices in cubic system. And later it is extended to other fields also. So the production of X-rays is basically very simple, and it consists of X-ray tube. So a small coil which is heated, so the electrons are released, and opposite to it you can place a target material such as molybdenum or copper, and you can apply a very high voltage such as 40,000 or 50,000 volt, and so the electrons are actually accelerate towards this anode material, and because of the high energy of the electrons, so the electrons move to the inner shells of the target material, and they knock out innermost electrons such as in K shell, so that the outer shell electrons will replace those electrons by emitting very huge amount of energy, and that energy falls in X-ray region, and therefore we get X-rays. So characteristic X-rays are obtained by using a suitable target material such as carbon or molybdenum. So diffraction is a very simple phenomenon. So we observe this, we know the difference between interference and diffraction. So Newton rings or airway deferment, we know that it is the fringes are formed due to interference. So for the diffraction, so you need the size of the aperture or the slit and wavelength of the radiation must be small equal. Suppose if you observe the open window, the light during night, so you may not find any difference. But if you observe the light through a curtain, for example, and you can see this type of pattern. So light undergo diffraction because the curtain is having small pores, and those size is equal to the wavelength, approximately equal to wavelength of the light. So the diffraction is something like this. You can observe diffraction something like this. So same manner in case of crystals also, crystals having the atomic planes, and the distance between the two planes is very small, so that it lies from 2 nanometer to 5 nanometer. The wavelength of the X-rays is also from 1 nanometer to 2 nanometer. Sorry, 1 angstrom to 2 angstrom, and therefore we observe diffraction. So whenever X-rays pass through the crystalline planes. So we use single crystal diffraction technique and powder diffraction techniques. So both are very important for analyzing the structure. In single crystalline diffraction technique, we use a single crystal, a tiny single crystal, which is of size of just a millimeter or even less. And in powder diffraction technique, we use polycrystalline material. Here, sample preparation, you need to grow a defect-free crystal by using some technique called slow operation. In powder method, you can use the sample as it is, but it should be in the form of a fine powder. So in powder diffraction technique, so we place the sample, the powder, in the sample holder, in the goniometer, and we rotate both X-ray tube and detector. So this scan is called coupled theta and 2 theta. So the angle at which the X-ray source is moved is theta, referred as theta. The angle at which the detector is moved is actually 2 theta, because it is measured with reference to the incident beam. So we get a diffraction pattern from this, because we have a powder particles are actually here powder, where you have the hundreds of small tiny crystals. When the X-ray falls on these tiny crystals, so these crystals will diffract collectively, and whenever the Bragg condition is satisfied, so the diffracted beams will be detected by the detector, and the detector will actually record the information in the form of intensity versus 2 theta. So X-ray source and detector are moved together, and diffraction pattern is recorded with the help of a detector, and it is stored digitally, and data is analyzed. So this is how actually the experiment involves. It's a very simple technique, powder X-ray diffraction method. You take the sample and you grind it thoroughly and make a very fine powder, and then you subject it to powder diffraction experiment. And here hardly sample preparation is just grinding, but no other treatment for the sample. So you just place this powder in the sample holder and just pause the X-rays, and then you can actually record the scan. So this technique, the powder diffraction technique, is very efficient and very quick, and it is able to, we are able to quantify, also we able to identify the crystal system properly. See, the silica exists in 3 forms. So one is quartz, and another one is cristobalite, and silica gel. So silica gel is amorphous in nature, and cristobalite and quartz are different. So one is tetragonal, another one is the hexagonal. So the hexagonal cristobalite has the pattern, different pattern compared to the quartz. And here we can notice that the powder diffractometer identifies the exact phase of the material. So we can quickly identify whether the material is quartz, or whether it is a cristobalite, or whether it is a silica gel. So we normally amorphous materials do not show any peak at all, because they do not have regular arrangement. Whereas the crystalline materials, other crystalline materials with a different symmetry, they actually give a particular peak pattern. By looking at the peak pattern, we can actually identify the material, because we can match this with the database. And in the database, we have structures, standard material structures. And when we match our experimental peaks with the database, we can quickly identify what type of material it is. This is actually called phase identification. So therefore, the powder diffraction pattern is a fingerprint of a crystalline material. So XRD analyzes crystalline composition of a sample, and it is not an elemental technique. So you cannot just judge from these peaks which element is present and what composition it is, so on. So further, we need some other technique, complementary technique, to do this, or we need to do a Rayfield analysis to know the structure information. What basically we concentrate in powder diffraction technique is peak location, peak shape, and intensities, relative intensities. So these informations will give the complete information about the atomic arrangement, as well as the phase method, and even the quantity. So quantitatively and qualitatively, we can actually identify the composition. If we have a mixture of many solids, that also we can identify, because we concentrate on these peaks, positions, and their shapes and intensities. Another important information we get, so we can use a Scherer technique, Scherer formula, to know the crystallite structure. So crystallite, it's not particle size. So average size of a small crystalline material present in the sample can be quickly calculated using this data by measuring the full width of it. Suppose this is a high intense peak in the powder XRD pattern. So what we can do here, so we can measure the full width of maximum. So you can use this information in this formula, where K is a constant, lambda is the wavelength of radiation used, and theta is the Bragg angle. And by substituting it, you can actually determine the particle size. So the application of this is, so this is some sample supplied by industry. So it is an analyzed sample, so using powder pattern. So they actually submitted the floods for mineral. This is the raw material used in used for dishwash powder by Sabina company manufacturers. So they are interested to know what is the percentage of silicon and free silica present in the sample, because they have to maintain these two, silicon and quartz, that is free silica sample, to a minimum level. So they submitted a raw sample, and I have analyzed this, and these are the results obtained. So it consists of different minerals, albite, anorthite, microclean, and orthosilate, orthoclase, silicon, etc. And so you can actually quantify all of them. And the analysis gives you what percentage of mineral is present. So in the mixture raw material. This is a raw material, and so therefore you can quantify. So here 8 phases are there nearly. No, 7 phases are there. So some of them are high and some of them are low. So here you can clearly quantify using this powder diffraction technique. So that is the importance of powder technique. It's very quick and versatile and give result so very quickly. And another technique is you can actually study the structure of the material also using this technique. So what we have done in this case, I am just showing one of our recent work. So we actually concentrated on designing the tungstate material, gadolinium tungstate material. So what we have done here, we have just incorporated sodium and potassium. So it is a lithium, sodium, gadolinium tungstate, and another one is lithium, potassium, gadolinium tungstate. And you see that it has actually, we observed, we have just modified sodium, we replaced the sodium with potassium. But the sodium gave different peak pattern, whereas the potassium gave a different pattern. It clearly suggests that the phase of the structure of sodium is different and the structure of potassium substitution is different. So it is basically, one is tetragonal, sodium crystallized in tetragonal phase, whereas potassium crystallized in monoclinic phase. And we have just identified the space group here. It is 82 and 15, monoclinic C2 by C. This is the I4 bar. And this is the arrangement of atoms. So gadolinium, tetragonal, and monoclinic structure. So what is more interesting here is, so we have just changed sodium carbonate. We use sodium carbonate along with these raw element, and it leads sodium tungstate. This is the potassium tungstate. If you use potassium carbonate, monoclinic, and it has shown the optical property, enhanced optical property. So without K and N, we have got very less emission. Suppose if you excite the sample using UV radiation, that is about 395 nanometer. So the emission, it emits the light. The sample is a better host material. Tungstates are actually regarded as the better host for lighting application. So this can be used for LED designing application. So here we observed that without sodium and potassium, we got a very little intensity, this curve. And the sodium has actually enhanced this intensity. So it is activator, sodium is activator. So its presence is actually increased the efficiency, emission intensity. So by many folds. So this is because of the structure. You can see here the tetragonal is actually favoring more compared to the monoclinic phase. So this is our XRD system in our college. We have Ruka D8 Advanced. So we have well equipped the system and with all these features. I will just give the details at the end of this presentation. Now I will just quickly take upon the single crystal technique. So single crystal diffraction technique is another method, versatile technique, more accurate, because in powder techniques we come across only one dimensional information. Everything is recorded into two-dimensional because it is intensity versus 2 theta plot. Whereas in single crystal diffraction, we get a three-dimensional information. So we need to have a better single crystals to be grown by using suitable techniques. And we have to subject it to a diffraction experiment by placing this small tiny crystal, single crystal, on a goniometer circle. And then it is rotated in a 4 circle. Anyway, I am not able to show you all the details here, technical details. But we can solve the structure from the diffraction data and it can we can observe the structure, crystal structure, complete crystal structure, and its packing within the event cell. So how we can grow the single crystal? So we have some methods like slow operation, vapor diffusion, cooling and temperature gradient. We need about 0.5 mm at least the size of the crystal. The crystals may be sometime block type, it may be needle type, each available. So these are actually called as single crystals. These are actually organic crystals. So we can grow organic crystals easily compared to inorganic and other type of crystals, metal organic crystals. And then the crystal is actually single crystal diffractometer is actually used this type of instrument. So here the tiny crystal is mounted somewhere here with the detector setup and the X-ray source. And this is the CCD plate, image plate, where we observe the diffraction spots, which is collected on a CCD plate and the image. So we collect hundreds of such images by rotating, oscillating crystal in all possible orientations, and so that we collect the lots of data. And finally, it is processed. And after processing, we get structure factor, FHKL. And using that, we identify the location of the atom in terms of electron density. So many structures like penicillin, vitamin B12, insulin, so all are actually determined using this single crystal technique. So, but identifying the location of atom is not sufficient. Now it has become routine. But we also, it is important now to understanding the packing, because if a structure is determined, it's not that you can predict the crystal structure. So crystal structure is so unique that the different samples will take different orientation, and therefore the symmetry and arrangement of atoms is different, and we cannot predict or we cannot guess. And therefore, what actually makes this different is because of interactions in it. So among such weak interactions, apart from covalent bond, we have the molecular interactions. Among the molecular interactions, the strongest interaction is hydrogen bond, and it may be OHO or NHO type of hydrogen bonds, or it may be pi interactions, or it may be stacking interactions, or even it may be the halogen-halogen interactions, which are actually very weak, but they also contribute to the towards the packing. So what these interactions will actually do? So these interactions basically will responsible for different packing patterns or different symmetry within the unit cell. So understanding such intermolecular interaction in context of packing and utilizing them for desired properties is basically a area called crystal engineering. And this crystal engineering is actually a field which is actually identified by and first time recognized and its importance, and it is this field was explained by the J.C. Raju. He is a pioneer in this field. And what J.C. Raju did, so whatever structures were deposited in databases, he used them, analyzed them, and he showed that so the different packing patterns can be altered and modified using some specialized techniques. So you can actually engineer these interactions for desired application, and you can design different materials with these available interactions. This is actually called the intermolecular interactions. So we have actually recently we are communicating a paper, and here you can see that we have used two co-crystals. It is the pyrazine, and the another is 2-chloro benzene ring here. See here we observe that when we use different temperature conditions, the structure of the material has actually changed to P21 by N to P21. Actually, both are monoclinic only, but the packing is different. I think you can check here. You can observe here. So structure one is PE phase, ferroelectric phase. It transfers from piezoelectric to ferroelectric. So this exhibit a property called piezoelectric, whereas this exhibit a phase called ferroelectric. And now today we also have some quantum mechanical techniques, and we can couple them with the X-ray diffraction technique, and we can actually understand the presence of distribution of the electrons, so within the unit cell. And therefore we observed that the elongation of the hydrogen bonds elongated hydrogen bond is responsible for the ferroelectric phase, whereas the normal hydrogen bond is responsible for piezoelectric phase. And this is also revealed by using quantum techniques. So, and charge density analysis. I'm not able to show all the results here because it's not relevant in this case. So, like this, we can use the crystallographic techniques and we can fine tune the properties by modifying some of the parameters, and by observing different interactions, we can predict its application. Another important application of the single crystal X-ray diffraction is the drug design. So the drug design is basically we can understand the drug activity by using a lock and key model. So if you have a proper lock, proper key, then only you can unlock or you can lock. So here the substrate is a molecule and the lock is a enzyme. If this substrate perfectly fits and reacts with the enzyme, then it will nullify its activity, minimize its activity. So this is how actually the drug works. So you have a drug molecule here, it's a small molecule, and this is the active site of the enzyme. And if this substrate go and fits in the active site, so then enzyme substrate complex forms, and the activity of this enzyme now becomes poor, so that it can now we can use this. And what is the method available now to determine structure? For enzymes and proteins, we use macromolecular crystallography techniques. Substrate or drugs, we use small molecule techniques. And by determining precisely the three-dimensional structure of both enzyme and substrate, we can actually design the drug molecules. Or you can use the database and you can screen the available structures from the database with available structure of the enzymes available in protein data bank, and you can predict whether it will act as a drug or not. So, because pharmaceutical industries nowadays are using these diffraction techniques than the academic research, because most of the drug molecules available in the market are the solids. So they are available in tablets and capsules. So the crystalline materials are well-defined three-dimensional architecture and symmetry, whereas amorphous materials they do not have. So therefore, the crystalline materials they are actually very useful in designing the drug molecules. So you can see why crystalline metals are so important. See, I am just comparing now the two different the chemical compounds. See here, both of them are differed just by one group. Here NH2 group is there, here NO2 group is there. NO2 group molecule is inactive, whereas NH2 group is active. Because here hydrogen donor is there, but here it is acceptor is there. Now this molecule is ready to bind with enzyme and it can show some activity, whereas this is a poor material, cannot be used. Even similarly here also, you have another structure. We have its methyl group, and here you have two methyl groups. The two methyl group, the compound is inactive, whereas one methyl group is active. See, this is the aspirin structure of the aspirin, acetyl salicylic acid. Commercial drug name is aspirin. It's a well-known drug. And this is a pain reliever, fever reducer, anti-inflammatory, anticoagulant. And this aspirin available in 7 forms actually. So 7 forms, but all 7 forms are not act as a drug. Only 2 forms are active. So these are the analogs of the penicillin. So penicillin. So this is basically a general formula for penicillin. So this is another group, and this is another group. So this is another group, but this is commercial drug amoxicillin. So which is available. So this is penicillin 5, maybe taken orally only. So like this. It is because each one of them will have a slightly different activity. Actually, the generic medicines available now for low price, the basically of this type. So because we cannot buy the patented drugs, so the government has allowed pharmacy companies to modify the existing drug. So they slightly modify the drug by attaching some other group, which is slightly different from the commercial patented drug, and so they can sell it for a low price. So generic medicines are basically of this type. See, these are some other types. So, but why the medicine companies time to time change their drug composition? Because all the drugs are having some issues, either solubility issue or toxicity levels are high, or it can affect, it has some other effects also. So no drug is 100% safe, and it will not have zero toxicity level. So therefore, their R&D teams will continuously work, and they design new materials with the new compositions, slightly modifying the group and minimizing the disadvantages. So antibacterial drugs generally have they are referred as sulfa drugs. So they have this type of group. Sulfonamide is a very well known drug. So these are the recent drugs which are derived from structure-based methods. So using extra crystallography technique. So anyway, these are some of the drugs used for various diseases, Tamiflu, so on. So proteins also can be protein structures also can be studied using X-ray crystallography, but proteins are actually a big crystals. So proteins are grown using this type of technique, hanging drop technique here, which is referred as. So we place protein, soak protein in using a suitable buffer and additives and sometime even metals, and so it forms a small crystal. And these protein crystals are very fragile. So because protein can survive only in the water environment. So if you remove completely water, the protein will die. So most of the protein crystals are having water from 30 to 70%, and the remaining is the protein. So once the crystals are formed, so we can use series of crystals and we can conduct X-ray, because as X-rays interact with protein crystal, the crystal will damage because of very high energy of protein. So we can have the structure, and it can be visualized as the cartoon diagram. So these are the latest Nobel Prize winning structure of ribosome. And spike protein, COVID protein, and you can check all these structures which are freely available in protein database and crystallography open database for small molecules. So all the properties details will be available there. So who actually determined the structure, what method they have used, what are the coordinates, and you can even download the file containing atomic coordinates. So these are the future techniques. So X-ray microscopy and the CT scan. See, using X-ray microscopy, you can visualize the matter inside any material. This is a battery material. You can see the battery material, and this battery material can be visualized using X-ray microscopy using this technique. And CT scan is another technique. Like in hospital, we use CT technique for patients, and same is used here for visualizing the materials. So this is developing techniques. So in future, I think we may have this type of techniques for visualizing even nanoparticles also. As a part of the International Union of Crystallography Year of Crystallography 2014, we also MSRIT is also organized a conference, 2-day conference. I think there are about more than 100 participants or participated all over Karnataka, and we are fortunate to have Professor Desiraj as a guest, and he actually at that time he was the president, IUCR president. So he's the first president for International Union of Crystallography. So after it is started, where the W.L. Bragg was one of the president for many years. It's really an honor to have him in our country. So because he developed a new field called crystal engineering. So and he wrote many popular books, and he is having highest citations in this field at present. So even Professor T.M. Guru Rao from ISU, the well-known crystallographer, attended, and these are some of the participants. So we have also organized a conference in this contest, and our college has supported for this. And in crystallography in India is not very new, and there are a lot of contributions since from 19th century beginning. So even C.V. Raman himself was a crystallographer in earlier days, and Kedareshwar Banerjee, and so they have determined the structure of naphthalene or anthracene. It's commonly purpura, the composition, and C.N.R. Rao. So Ramachandran, A.R. Verma, Ramaseshan. So they also contributed. See, this Kedar Ashwar Banerjee is having another contribution. So he is first time he talked about direct methods which we are using to determine structure of simple single molecules. The first uh, uh, he has actually started working mathematical model which is called direct methods. But later on, somebody else from the abroad who actually got the Nobel Prize for that work, but his work was not recognized. So, but his contribution is immense. And even G.N. Ramachandran also. So he revealed the structure of triple helical structure of collagen, the most abundant protein in our body, like it present in hair and strong other organs. So here, the Ramachandran independently worked in India, and just after double helical structure by Watson Crick, that famous DNA molecule, he actually determined the structure of triple helical structure. So he just published it, but his work is more or less equivalent to the double helical structure, because this is triple helical structure. It is much more complex than compared to the double helical. But he missed a Nobel Prize because his contribution was not recognized. But later on, so he also worked very hard to show that what are the allowed interactions present in the proteins, that is such as peptides. So in terms of this phi and psi map, which is nowadays it is called as Ramachandran map. Suppose if anybody want to recognize structure of protein and its stability, so this Ramachandran map is it's a tool to validate the quality of the structure, and it shows the allowed regions and disallowed regions. Means it is the proper orientation and interactions leads to formation of the phi and psi angles. The phi is the angle between the elongated N and C bond, and C and C bond shows another angle, gives another angle, planarity, and that is phi angle. So his student Ramachandran and Venkateshan, both of them helped in assisting him, and they also worked for the multi anomalous dispersion and single phase anomalous dispersion techniques, which are now very useful in determining the structure of the macromolecules. Coming to this, so I have fortunate to interact with these people. So now all of them are retired. Professor Desiraju, retired professor, and Professor T.N. Guru Rao. Because of both of them and Imran Murthy and I have just learned the crystallography basics properly. So because I have associated with them almost more than a decade, and the T.N. Guru Rao is extremely grateful to him because he allowed the diffraction facility to carry out my experiments in his lab. So this is the powder diffraction facility available at our institute, Bruker D8 Advanced. So equipped with 2.2 kilowatt extra source. And even we have a SAX facility in this instrument. And apart from that, we have the softwares and database also, ICDD database. So we charge for externals with a nominal cost about 400 rupees per sample. Also, we encourage young students, PG students or even degree students to carry out their project at free of cost. So they can come to my lab and they can work for maybe a week or 2 weeks. And we have all the synthesis and characterization facility apart from XRD. So if anybody interested can come to college, or you can just mail me. So, and whenever you have free time, you can come and you can utilize our facilities. And we encourage especially students and research scholars of whoever is in the audience. So you are free to come at any time and you can utilize our facility. And finally, I will thank these people, my mentor and my guide, Dr. Kokla and Dr. Puttaraja, for their teaching. So because of them only, I have just interested in crystallography, because Puttaraja was a great teacher and he used to teach the basics, especially symmetry and crystalline systems and techniques better than anybody else, and even T.N. Guru Rao. So I have attended his some of the lectures, and he allowed me to use facilities in the ISC, and Professor M.E. Kulkarni for interactions. And I was poor in chemistry, and His discussions helped me to understand chemistry of the materials and completing papers, and Institute of Technology for encouraging me and providing facilities. And I would like to thank all my collaborators who directly indirectly helped me, and my students, PhD students, and my project students. And finally, I thank one and all for your patience listening, and thanks for spending your valuable time and understanding just a few information about the crystallography. Since it is a very vast field, I just covered only two techniques briefly for about 30 minutes, 30 to 40 minutes. And it's time to take questions if anyone is having. But I'm not able to hear the sound still. I don't know what's the problem.
Okay, sir. If any questions, you can
Hello.
type in the box.
Okay. I'll just 1 minute. I will disable my mic and I'll reconnect. If it permits, then.
Am I audible, sir?
No, I can't hear you. Can you hear me now?
We are able to hear you, sir.
Yes.
But
Now I disconnected my hands on. Okay.
we can take questions, sir.
Yes.
Okay. Any question from participation? You can ask the questions, or you can type in chat box.
Anil, I'm Srinath here. It's a very good presentation. Hope you are hearing my voice. Anil? Supriya madam, can you hear my voice?
Yes, sir. Anil, sir, you are muted.
Anil, are you hearing Anil?
Sir, you are.
Can you hear me now?
Yeah.
Yes, sir.
It was a good presentation. Simple question only. You have explained for the especially amorphous powder and the other solids. Just out of curiosity, certain liquids like petrochemical detection or any such kind of area, whether this crystallography, what is, I mean, is it successful or failure? What is the possible?
It is successful now only. So we have a complementary technique now called pair distribution function. It's applicable to amorphous materials. This pair distribution function I have not included in my presentation. Pair distribution function gives the local arrangement of atoms or molecules. Suppose if you have a cluster of atoms, for example, and you can concentrate on one atom and you can reveal the neighboring atoms and their arrangement. So pair distribution function is very useful in understanding the interactions or the structural information of amorphous materials, certainly like glass and nano composites. And there is another technique called X-ray scattering. Normally these materials like solutions, if you have a suspensions like very minute particles and nanoparticles in a medium suspension, you can actually use X-rays. These materials are not like crystal. They do not diffract, but they scatter X radiation at very low angles, maybe from 2 degrees to maybe 10 degrees maximum. So you pick up the scattered X-ray radiation, and using that technique, we can actually use, we can reveal the information like the molecular weight. We can determine the molecular weight of proteins. For example, you have a protein solution, you can use X-ray scattering and you determine molecular weight. And whether you can, it is a uniformly distributed or randomly distributed, that information also can be obtained. So these are the informations we can actually get from the small angle and wide angle X-ray scattering techniques. Here, the principle is not diffraction, but it is scattering.
Okay, thank you. Since here it is an active source, any other like passive source based crystallography is available?
Sorry, can you?
Now, when I say active source, you are pumping the X-ray
Ah.
on a crystal and then you are studying.
Hmm.
Are there any materials which are emitting X-ray and then studying similar fashion? Is one question.
No, X-rays, we know X-rays from 1900, but in an extrastellar space, already X-rays are there. So we actually, in our labs, we are using X-rays from just 100 years. And we have today free electron laser sources also, and synchrotron sources, which are much powerful than laboratory X-ray sources. I think if you spend hours in laboratory X-ray sources, but the same data is obtained in synchrotron and laser sources in few minutes, because their intensity is very high. So those techniques are actually will replace, I think, in future.
Thank you. Thank you. Others can ask questions. Supriya, about you.
Okay, thank you, sir. Any more question? You can unmute and ask the questions to sir.
Sir, namaste, sir. Anil, sir.
Madam, namaste.
Jyoti, sir, from Chintamani. Hello.
Madam, tell me, madam.
Sir, when we have to use neutron diffraction and electron diffraction other than
Okay.
X-ray
So
diffraction?
neutron diffraction, so because X-rays are not scattered by hydrogen atom. Hydrogen atoms contain only one electron. Basically, if electrons are more, so then we observe X-ray diffraction, proper X-ray diffraction. If electrons are less in a particular atom, then diffraction is very poor. So hydrogens are having only one electron, and we hardly get diffraction from hydrogen atom. So because scattering factor of hydrogen atom is only one. So if you take any atom with 50 electrons, it is 50 times more powerful scattering ability than hydrogen. So sometimes we are unable to locate hydrogen atoms. Actually, in protein crystallography, they neglect hydrogens completely because that information is completely unavailable. Whereas in small molecules, if hydrogen bonding is very important, then we can go for neutron diffraction. The neutrons will actually interact with the nucleus of the atom, not with the electrons. So we get the diffraction from the nucleus of the atom itself. So hydrogens also will diffract properly if we use neutrons, and that is actually the purpose. And coming to this electron diffraction, electrons are having energy, and we can tune electron energies much lower than X-rays. Much higher than X-rays, and wavelength is much lower than X-rays. So we get more information than X-rays if you actually use the electron diffraction. It's a emerging field now. Already a few companies like Rigaku have launched electron diffraction equipment. And, so it is equally, more or less equally important like X-ray diffraction only. Analyzing and interpretation is very similar to electron only. X-ray only. But in electron diffraction, we just replace X-ray with electron because we have an advantage. We can tune the wavelength depending on the sample. So that's the advantage we have in electron diffraction X-ray.
Okay, sir. Sir, many of the participants are our students. So they want to know about the softwares which are used in powder XRD.
They want to know?
Softwares and programs which are available to study.
I think for analyzing powder diffraction, there is a suit called FullProf, FullProf, and it is containing many packages. It's actually a package contains many softwares, visualization, analysis, and many other. And commercial software is also available. Free software there are many. So this FullProf is the most widely used software, and MAUD is another software which is more convenient for beginners. Like so many other software. I think you can just Google it, you will get many other software. I think these are the two comfortable for anybody. These are the two softwares which are very comfortable to handle.
Sir, how we can study the electrical properties, sir, like piezoelectric, ferroelectric properties after determining the structure?
No, this is not with X-ray technique anyway, but it is with the optical and other techniques. So you can study this. And you apply electric field and you can see the response. Based on that, we actually predict that property.
Okay, sir. Thank you, sir, for the wonderful presentation.
Thank you very much, ma'am.
Any more questions?
So once again, I'm just telling, so we have the facility, auto diffraction facility and other facilities in our lab, like CAMT lab. So if anybody interested, so as I told you, so you can contact me and you can utilize our facility. And we encourage students to do the projects.
Supriya, you
Especially
can
I
ask,
already
if
helped
not-
many students.
people can give comments and remarks, sir. By name, you can ask them to unmute and ask if they don't have questions. Dr.
Sita
Sita
ma'am?
Madam.
Yeah, I already typed my appreciation on the chat box because I was not able to hear. Very, very informative talk because we learned a lot of things on applications which are very timely and which are very recent. For example, on the drug, etc., and what is the difference between the various types of things. So it was extremely informative. Thank you very much, sir, for the
Thank you very
wonderful
much.
talk.
Thank you very much.
Yeah, thanks a lot.
Madam, others,
Dr. Shruti ma'am? Any comments, ma'am?
Yes, it is very informative talk, and it is very actually it is very trendy talk. It is very recent research is going on all this. So even sir explained the powder XRD techniques and the usage of all those things, not only single crystal. So it is very up to the mark. It is a trendy topic, ma'am. I thank the organizer and also the session presenter, today's session presenter. It is very informative. Thank you.
Anybody likes to comment? You can unmute and
ma'am?
you can. Yes, Ganesh.
Sir, my name is Ganesh. So I'm present. I'm doing MSc first year physics in Gnana Bharati. So in future years, I'm so interested in doing my PhD. So what are the guidance for like students like doing PhD for in future years, sir?
PhD, okay. I think now options are more. What you can do, one direct method and another indirect method. So I just refer like that. Direct method is you take the exams conducted national level by various institutes. Altogether they conduct it and like just and GATE or CSIR exam. And if you get better score, JRF, if you clear JRF, you can join any of the institute of your choice. Because stipend is now, they give stipend more than 40,000 and other allowances also. This is one method. Suppose you are unable to clear this, don't worry. So you can join any of the lab under any professor as the project assistant. And if you get a better training as a project assistant, and they will encourage you to publish papers. If you have good papers, one or two, they will recommend you to do PhD abroad. So in abroad, they consider the recommendation from reputed scientists from reputed labs. So you can actually apply for it, and you can actually join, and you can complete PhD in any of the reputed institute abroad, Europe or even US and in other countries. I will just tell you one example. There's one student from Amity University who actually came last year. I don't know how he came over to me. He just mailed me and I just agreed. And he has worked with me just for 1 month, but he is very interested in doing research. But he somehow he actually found some contact abroad. He just asked his guide and for me for a recommendation. I don't know my recommendation helped him or other. I just gave formally the letter, and he has now selected, and he is actually pursuing a project in Netherlands. Like you have options like this. So it's not the and there are some other universities abroad. They will conduct their own exams online or interviews online, and they will recruit directly. But these are some of the options. Actually, there are various options. There are some good institutes available now nearby Singapore, even Malaysia, Korea, where language is a bit problem. But you can look for US and European countries also. Lot of options available. I think you can join some groups. Even you can use the Twitter or kind of thing. You can follow some of the professors. They will announce these positions and all. Even in Facebook also. I think these days people are fond of following unnecessary people in Twitter and Facebook. If you follow good scientists all over, I think you will get this type of information. I generally update myself by following Twitter and Facebook accounts, especially whoever is good in this field. You can make use.
Thank you.
Sir, one more question in chat box.
Nagendra,
Sir.
Nagendra asked, why do we observe peaks of different heights in XRD pattern? It is depending on the symmetry and nature of the atoms, you get peaks. Some are very intensity is very high, some are very low. Generally, if you take metals, for example, the intensity will be very high. So because because the density is very high in such cases, in case of metals. Even inorganic materials also, nano samples intensity will be low some extent. See what decides this height, it is the symmetry and as well as the packing of atoms within the unit cell. So it is crystalline. See what we observe basically in XRD pattern is, from the XRD pattern is crystalline state, that's all. Crystalline state, not composition, not elemental information, so on. Whether it is crystalline, which type of crystalline state? Let us say, for example, it is a triclinic system, cubic system, or monoclinic system. If you further deeply analyze, you get the information of atomic packing. So that is the information we get from XRD pattern. I think Nagendra is clear, right?
Yeah. Yes, sir. Any more questions? We got the answer, sir.
Okay, thank you.
Any more comments? Okay. So shall we wind up, sir?
Sure, madam, sure. So thank you very much. I congratulate the creative team because they're constantly organizing this every week, and conducting this type of talks is not very easy. Actually, I just remember when I completed my MSc, I used to go to National College Baswangudi in July, whole month, because Professor HN was there, and he is taking all this pain in organizing and calling reputed persons. I think first time I heard many of the good lectures there. That is the inspiration. I think now you are using technology. At that time, there is no any visual tools or even electronic sources to get the information. So only they used to send the information through letters only for display in departments and institutes. So I think it's very difficult. Such time, I think he has constantly, Professor HN has actually organized these things. It's not so easy. And now you are using these tools and constantly you are organizing this. I think both are equally good. So even though HN is not there, I think we are actually spreading this knowledge in Gauribidanur town. That is very, very.
From his inspiration only we are working, sir.
Yeah, he is inspiration to all of us.
Yes, sir. Yes, sir. As being a National College students, it's our duty also. Ma'am, Sita ma'am, you like to ask any questions?
Yeah, just I wanted to inform him, sir, on a satellite called AstroSat, we have flown X-ray optics, that is grazing incidence X-ray optics, because these can't be reflected easily like a regular optics. So Tata Institute of Fundamental Research developed this optics, and with aluminum foils with a gold coating, and we have flown that with a CCD detector, which actually does X-ray spectroscopy of stars and stellar systems. Just wanted to inform you about astronomy with
No,
X-ray,
I
sir.
heard this because in one of the Guru talk, I heard this. He was also involved, I think, invited for AstroSat project, I think.
Yeah, and recently in Chandrayaan 2, there is an experiment called CLASS, which actually uses same X-ray spectroscopy, actually fluorescent spectroscopy. Incident X-rays are from the sun, actually. Solar flares, incident on the moon soil, and then the moon soil fluoresces, and that spectra we observe and then identify the elements.
Yeah, it is basically.
So that is again done by Shama Narendranath. I don't know if you know her. So
Yes, madam. It is
yeah, just wanted to inform you. That's all.
No, it is another great achievement, and it is actually X-ray microscopy. What you told about, and X-ray diffractometer is already used in Mars rover, NASA. Actually,
Yeah.
that paper, published paper is there. It has given results. What minerals are there already? It has published actually. So diffractometer, very minor diffractometer was actually sent.
Yeah, we do spectroscopy. We call it spectroscopy because we study the fluorescent spectroscopy. So
yeah. X-ray fluorescence. Yes.
Yeah.
Thank you, madam. Thanks for the information.
Thanks a lot, sir.
Yeah,
Sir, one more question.
Meghana Varun is asking, can we deduce the structure of DNA using X-ray crystallography? Yes, the Wilkins and Dorothy Harkin. So they actually crystallographers involved in Watson Crick model. So Watson is not a crystallographer, but they took nearly 1,000 photographs, which revealed helical structure. It is actually called fiber diffraction. So even you can go for diffraction of the fiber kind of material using that technique. So it is a fiber diffraction. Yes, we can reduce structure of any such fiber, any spherical, like the spiral kind of material, like cotton fibers, even some macromolecule fibers. So can be analyzed using a similar technique. Yes, it is also diffraction. I think is it clear?
Meghana, you got the answer? Okay, sir. It's already 4:25, sir. Shall we wind up here, sir?
Sure.
Sir, we are very happy. Sir, one more. No. Okay. Thankful message.
Thank you very much, Anirudh, for your comments.
Sir, we are very happy for the session and for your insight knowledge. I thank Anil sir for your time and dedication towards us. And I thank all the participation for your presence, questions and discussion with Anil sir. Thank you one and all for joining us. Thank you.